This is section 4.5. We're going to be learning the superposition principle. So we're going to jump right into it here. The superposition principle says that if y1 is a solution to ay double prime plus by prime plus cy equals f1, and y2 is equal to the second equation where the left side is the same, but the right side is some other function of t, then for all constants k1 and k2, we have that a linear combination of y1 and y2 is a solution to the same equation, the same terms on the left, but it's a linear combination of the f functions on the right. This will make a bit more sense when we start to use it, but we'll first go over the proof. It's simple enough. If you plug in k1 y1 plus k2 y2 for y into the left side of this equation, well, you can take out these constants when you actually take the derivatives. And then when you set aside the k1 and the k2 terms, it does turn out that, well, this is equal to f1, and this is equal to f2. So we have k1 f1 plus k2 f2. So this is a way to make solutions to equations based on solutions to other equations without actually doing any extra work. So let's see how this works. Find a single solution to both of these equations. Y double prime plus y prime plus y equals 2t e to the t plus t, and y double prime plus y prime plus y is equal to negative 4t e to the t plus 6t. So let's start figuring out what is what with respect to our superposition principle. So this is a sum of two different terms here. We have 2t e to the t, and we have t. Now, our second equation, the right side of that, negative 4t e to the t plus 6t, is just a linear combination of this, multiplied by negative 2 to get to negative 4t e to the t, and we multiply t by 6. So we are going to plug these values into our superposition principle, and we are going to solve y double prime plus y prime plus y equals 2t e to the t. Then we're going to solve y double prime plus y prime plus y equals t. And then we're going to use our superposition principle to take whatever y values satisfy these two equations, take a linear combination of them, and that will solve for our linear combination, negative 4t e to the t plus 6t. So we're going to start by working with 2t e to the t. So this equation right here is the first thing that we're going to solve. From our table that we've been working with on page 178, we're familiar with this form. And it's actually a fairly simple one where m and r are just equal to 1, and we have our constant 2 being multiplied by it. So our first step is always to look at the auxiliary equation when we're dealing with these things from the table. So our auxiliary equation, recall that it's just the values being multiplied by all the derivatives and the original function y. So these are all actually 1. So our auxiliary equation is just r squared plus r plus 1 equals 0. And our table on page 178 asks us to check whether 1 is a solution to it, and 1 isn't a solution. So we don't have to multiply by some s to the 1, some t to the 1 term. S is equal to 0. So what does our table tell us is the form then? It gives us a1t plus a0 times e to the t. Note that a lot of more complicated elements just aren't here. We don't have to multiply by some t to the s term. we don't have to have e to the RT. Some of these things just cancel out because we're dealing with such a simple equation. So it's just a1t plus a0 times e to the t. Now we'll take our derivatives. We've done this quite a bit by now where we're just taking product rules, but you can check your math against this. And then we're going to plug in y double prime, y prime, and y into the equation we're working with, which is y double prime plus y is equal to 2t e to the t. So this is what we get when we plug it all in, this whole line here. Simplify, simplify, simplify. And we get 3e to the t factored out, multiplied by a1t plus a0 plus a1 is equal to 2t e to the t. And recall that this 2t e to the t, that actually comes from the statement of the problem. Scrolling, scrolling. We decided that the first thing we were going to solve was with 2t e to the t as the right side of the equation. So that's what we've plugged in. Now, we can actually divide out by e to the t, and that's going to simplify things for us. And then we also divide both sides by 3, and that gives us 2 over 3t is equal to everything inside this bracket, a1t plus a0 plus a1. Then we're going to do what we always do at this point, where we have our t coefficient and we have just the constants, or just the extra values that don't have a variable involved. So a1 must be equal to everything on the right-hand side that's multiplied by t, which is 2 over 3. So we get a1 is 2 over 3, simple enough. But we also get a0 plus a1, these constants, have to equal, well, there's no constant on the right side, so it's just 0. So they have to equal 0. So a1 equals 2 over 3, that one's already solved, but now we have to plug that 2 over 3 in here as a1. So we get that a0 is equal to negative 2 over 3. So we have a solution. Y is equal to 2 over 3t minus 2 over 3 times e to the t. Now recall, this is just our first solution. This solved for 2t e to the t, but if we scroll back up, recall that this was a sum. It was 2t e to the t plus t. So now we're going to do all the same work again with the right equation just being t instead of being 2t e to the t. Sorry, the terms on the right, not the right equation. The whole thing is an equation, but the terms on the right just being t. So here we go doing it again. We're again going to consult our table. M is equal to 1, but now R is equal to 0. Now we're asked to check, of course, if R is a root of the auxiliary equation, but 0 is not a root of R squared plus R plus 1 equals 0. So our table tells us that Y is just going to take the form A1t plus A0. Nothing else involved here, no E's, nothing else. So when we start taking derivatives, actually, by the time you take your second derivative, everything is gone and we're just down to 0. So plugging these in will be much simpler. Y double prime plus Y prime plus Y. We just add up the terms that we just solved for. So A1t plus A0 plus A1 plus 0. And then we set it equal to t, because that is the part of the equation that we're solving this time. We solved 2t e to the t before, now we're solving for t. And now we have a1 being multiplied by t on the right side and 1 being multiplied by t on the left side. So that's an equation. And we have a1 plus a0 as a constant on the right, and we don't have a constant on the left. So it's just equal to 0. So a1 is equal to 1, and that makes a0 just equal to negative 1. So in this case, y is equal to t minus 1. Now that we have the solutions to these two much smaller, simpler problems, we're going to use our superposition principle. So we have that y1 plus y2 is just equal to these things that we solved for. 2 over 3t minus 2 over 3 times e to the t plus t minus 1. That is a solution to our first problem. The second equation, as we stated before, represents a linear combination of these solutions. Since the second equation is y equals negative 2y1 plus 6y2, we just plug in our y1 and our y2 values, and we get a final solution for the entire problem. Y is equal to 4 over 3 minus 4 over 3t times e to the t plus 6t minus 6. Once again, I'll remind you where the 6 and the negative 2 came from. If we go back to the original statement of the problem, we showed that if you multiply this by negative 2 and this by 6, you take a linear combination of things we already know the solutions to solve for the problem that we've been asked, where we set it equal to negative 4t e to the t plus 6t. So that's how you use the superposition principle. It allows you to add together solutions of smaller problems. So I was able to add together the solutions where the right side was equal to t and the right side was equal to 2t e to the t to get the solution of the sum. And then given the solution of the sum, I was able to evaluate the solution of the linear combination. And it's right there. Now we'll do another example. In this one, we're actually given a bit of information. We're given that sine of t is a solution to this equation. Y double prime minus 2y prime plus y equals negative 2 cos of t. And you can check that yourself. Actually, it's very quick. We'll do it right now. The first derivative of sine t is cos t, and the second derivative is negative sine of t. So if I plug that in to this equation, I get negative sine t minus 2 cos t plus sine t equals negative 2 cos t. And that's clearly true because negative sine cancels out positive sine, and the left side equals the right side. But here we've been provided with that. We don't need to resort to our table and do a whole sine plus cos calculation. To make things simpler, we were provided with that solution. But given that, we're asked to find a general solution and a solution satisfying these initial values. Y prime of 0 is equal to 0, and y of 0 equals pi. So first, we need to understand what it's even asking us. Before we get into the exact particular solution based on these initial values, we've been asked to find a general solution. Now, y equals sine t, that's not a general solution because that's a particular solution. There's no constant values like C1s and C2s. This is a very particular answer. But the superposition principle is going to help us here because we know that we can use the homogeneous solutions to help us. So think about the homogeneous version of this equation. The right side would just be equal to 0. So if you go back to section 4.2, when working with homogeneous equations, the first thing is to look at the auxiliary equation. And it has one solution, and it's actually a double root. R is equal to 1. So from 4.2, we get that a solution is y equals e to the t. And that's because y equals e to the RT, and R is equal to 1. So y is equal to e to the t. But since 1 is a repeated root, again, from 4.2, we get a second solution. Y is equal to t e to the t. So our general solution to the homogeneous equation is y equals c1 e to the t plus c2 t e to the t. Now we're going to recall the superposition principle. Since y equals sine x is a solution of this equation, and y equals c1 e to the t plus c2 t e to the t is a solution to the homogeneous equation, Then for all constants k1 and k2, I know what the right-hand side of this equation looks like. It looks like k1 times f1, which is sine x, plus k2 times f2, which is the thing we just solved for, c1 e to the t plus c2t e to the t. Now, what are k1 and k2? Well, they're just 1. We didn't multiply them by anything. So we have that y is equal to sine t plus c1 e to the t plus c2t e to the t by our superposition principle. Now we can finally plug in our initial values. Well, when y is equal to pi, t is equal to 0. That simplifies very nicely to just give us pi is equal to c1. Then we take our derivative. And we know that when y prime is equal to 0, t is equal to 0. We know that ordered pair exists. So we get c2 is equal to -1 minus pi. So we already solved for our general solution, but now our particular solution for when these 2 points exist is y equals sine t plus pi e to the t minus pi plus 1 t e to the t. For our next example, we're going to find a general solution to y double prime minus 9y is equal to cos of 2t plus sine of 2t. As always, we're going to begin by looking at the auxiliary equation. So that's r squared minus 4. Well, there's a typo right there. It's r squared minus 9. R squared minus 9 is equal to 0. So that gives us two values. R is equal to plus or minus 3. Now, by our table on page 178, we have a beta value of 2. That's what's multiplied by these t's. We have m equal to 0 and alpha equal to 0. That's because this is just trigonometric. There's no e's in here. It's not being multiplied by a power of t. And now our table asks us if I times beta is a root, and it's not. We have two real roots here. So I times beta is not a root. And because of that, s is equal to 0. That's going to further simplify our solution. Now, here's what we're going to notice based on this new principle of ours. Y double prime minus 9y is equal to cos of 2t, and y double prime minus 9y equals sine of 2t take the same form in our table, so we can calculate them together. And what we mean by that is they're both going to have some sort of solution that looks like a times cos 2t plus b times sine of 2t. So there's no point in calculating them both separately and then just adding the results together, because that's twice as much calculating. Let's just jam them all together and calculate it all at once. So rather than calculate both of these separately like we did with the previous example, we're going to do them all at once. So y is equal to a cos 2t plus b sine 2t, and that comes from our table on page 178. And now we'll take two derivatives. These are very easy. There's no product rules going on here. Now we'll figure out what y double prime minus 9y is equal to. That's just y double prime minus 9 of these. So that's what you'll see here, y double prime minus 9 times y. Now we perform our substitution, because we know in the problem that y double prime minus 9y is equal to cos of 2t plus sine of 2t. And we're going to move the cos over and the sine over so that we're just left with 0 on the left. And on the right, we get negative 13a minus 1 times cos of 2t and negative 13b minus 1 times sine of 2t. This gives us that both a and b are equal to 1 over 13. And so our solution is y equals 1 over 13 cos of 2t plus 1 over 13 sine of 2t. And in the past, we may have been satisfied that that is our solution, but by the superposition principle, we can get a more general solution, and that's by adding in the homogeneous solutions. So the auxiliary equation, if you recall, had two roots, plus or minus 3. So the homogeneous solutions, remember, that would be if we looked at y double prime minus 9y is equal to 0, and then we combined it with y double prime minus 9y is equal to cos 2t plus sine 2t using our superposition principle. Well, the auxiliary equation has two roots, as stated, so the homogeneous solutions are y equals 3 to the t and y equals negative 3 to the t. Just your R values. So our final, most general solution has the 1 over 13 cos 2t and the 1 over 13 sine 2t, but you also add in both of your homogeneous solutions, c1 e to the 3t plus c2t e to the negative 3t. And I'm seeing another typo, but typos are okay as long as we catch them. There is no t there. It is c1 e to the 3t plus c2 e to the negative 3t. And this is a solution. If you plug in c1 and c2 both equal to 0, well, it's still a solution. If you plug in c1 and c2 both equal to 1,000,000, or one equal to negative 1,000 and the other equal to 2, whatever, they're always going to be solutions. So you can read pages 183 to 185 in particular to really get a grasp on these steps. I feel there's a couple really good examples there. And there is an update to our methods from the table on page 178. So we have a table on page 178 that we're following. Well, we get even a new case that we can learn on pages 184 and 185. So I would advise definitely reading into that to get more familiar with that.